Without objection, the chair is authorized to declare recess at any time. Good morning. Welcome to today's hearing titled The Energy Water Nexus, Drier Watts and Cheaper Drops. I'd like to thank our panel of witnesses for being here today. I'd also like to thank both Chairwoman Johnson and Ranking Member Lucas for introducing the Energy and Water Research Integration Act of 2019, which addresses the energy water nexus issues that we'll be discussing today. I think it is tremendous that our committee's leadership has started this year off with a major piece of legislation that is bipartisan, and I commend them for that. The connection between energy and water is indisputable. It takes a lot of water to produce energy and a lot of energy to produce clean water. Large-scale power plants mainly use water as a cooling source. I've seen this back home. We have a nuclear power plant and a coal-fired power plant right next to each other in my district that use a lot of water on the Ohio River. A substantial amount of this is used to produce other common fuel sources like oil and gas, which produces a lot of wastewater. Also a significant issue in western Pennsylvania, where I'm from, where we have a lot of natural gas drilling taking place. The Energy and Water Research Integration Act of 2019 aims to decrease energy and water intensity when we use these resources by integrating water production, use, and treatment considerations throughout DOE's R&D programs. Reducing the water intensity of energy and the energy intensity of water production will help our environment, and most importantly, it should decrease the utility bills for our people back home. This is not a new field of research. Congress instructed DOE to create a program to address this back in 2005 with the Energy Policy Act, and in 2012, the Department created the Energy Water Nexus Cross-Cut Team. This created a plan for future work and research at DOEs. They have held a series of roundtable discussions, including some with the witnesses who are here today, and we thank you for filling us in on those. Unfortunately, this team was disbanded at the beginning of this administration. The administration has recently launched an initiative that focuses on water production and announced 2 new funding opportunities for desalination. But these are only some components of, I think, the overall nexus that we need to be addressing. So restoring a focus to this connection we view as crucial. Global energy consumption and water demand will continue to go up, and it likely will for decades into the future. This is exacerbated by climate change, meaning it's going to get worse and more difficult to solve, which is why I think we need a whole of government and, of course, bipartisan approach on this. The relationship between energy and water, we also know, is very specific to particular regions. In the West, when temperatures are high, water used for cooling power plants is much less efficient or not even available when there are severe droughts. Sea level rise affects the water sources along the coast, increasing the need for energy-efficient water treatment capabilities. Weather can affect the demand for energy, like the extreme winter weather events experienced back home in my district, where we have plenty of water, but often have some very cold temperatures. This threatens both the energy and water infrastructure. So efficiency measures would help mitigate all of these problems, and that's where our discussion will focus today. We're going to look at the nexus between energy and water, but also talk about some solutions that are innovative. One of the witnesses we have here today, Dr. Richard Bonner, has led many projects related to water use and energy production at a small business in my home state of Pennsylvania. So I will use my prerogative to welcome you, Dr. Bonner, as a fellow Pennsylvanian. We're thrilled to have you here. His projects have been funded through various government programs such as ARPA-E, which we view as a program that's vital to our energy research and development. We need more innovative projects like yours in this field, and we all look forward to your testimony. And now the chair recognizes my Republican colleague and friend, Mr. Weber, for an opening statement.
Thank you, Mr. Chairman. Today we will hear from a panel of experts on the challenges in the U.S. energy water nexus and discuss the Department of Energy, DOE's role in enabling fundamental research and development in support of these critical resources. A sustainable supply of both energy and water is essential to the maintenance of U.S. economic health, environmental stability, and national security. Water is needed to produce energy, and energy is required to extract, treat, and transport water. This fundamental and tightly intertwined relationship is often referred to as the energy-water nexus. We see the energy-water nexus at work in the production of fossil fuels and biofuels and in the functioning of thermoelectric power plants across our great country. Historically, energy and water systems in the U.S. have been planned and managed separately. Today, It is clear that no matter what the future cross-section of the U.S. energy market looks like or will look like, we will need to develop an integrated approach to these two systems. A number of federal agencies have supported research and development efforts related to the energy-water nexus, including the Environmental Protection Agency, EPA, the Department of the Interior, DOI, and the Department of Energy, DOE. With its strong expertise in energy technologies and world-leading, I might add, fundamental science capabilities, DOE is uniquely suited to lead the national energy-water nexus conversation. The department enables high-level use-inspired basic research that supports our understanding of today's evolving energy-water nexus throughout its national laboratory system. At the National Renewable Energy Laboratory, NREL, DOE funds research into a wide portfolio of advanced technology solutions to today's energy-water nexus concerns, including desalination using renewable energy technologies and the reduction of water needs for solar technologies. At the National Energy Technology Laboratory, NETL, DOE funds research in advanced cooling and water treatment technologies, non-traditional water use, and modeling tools to evaluate the impact of fossil energy development on both surface and subsurface water resources. And at Sandia National Laboratories, y'all have heard of that, right? At Sandia National Laboratories, researchers are focused on creating new water supplies using advanced technologies. Sandia also supports research that develops and provides decision-making tools to U.S. institutions that control the supply of and demand of both water and energy. Recently, the Trump administration has taken a number of steps to prioritize research in the energy-water nexus. In October of 2018, Secretary Rick Perry announced the launch of a DOE-led Water Security Grand Challenge, which will incentivize the development of new technologies to address critical U.S. water security challenges. Then in December, DOE announced $100 million in funding for an energy-water desalination hub focused on early-stage research and development. This hub will explore non-traditional water sources and provide desalination technologies that are both cost, competitive, and energy efficient. I want to thank the chairman for holding this hearing today and the witnesses for providing their testimony, and I'm looking forward to learning more about this important research in our hearing today. Mr. Chairman, I yield back.
Thank you, and the chair now recognizes Chairwoman Johnson for an opening statement.
Thank you very much, Mr. Chairman, and good morning and welcome to our witnesses. I'm delighted that we are holding this hearing. It's very timely to bring attention to the interplay between water, one of our most valuable natural resources, and our energy systems. Our energy and water systems are intrinsically interconnected. Not only does energy play an important role in the extraction, treatment, and transportation of water, but water is also used in many stages and types of electricity generation. In my home state of Texas, we face a multitude of issues at the energy-water nexus. For example, large amounts of water used during the process of fracking for oil and gas extraction. However, the needs of the large oil and gas industry can be at odds with the needs of the agriculture community, where farmers struggle to conserve water and energy to save costs, especially in the face of increasingly extreme droughts in the state. Of course, water is an important resource for energy and agriculture, but it's also critically important for the people. My own city of Dallas, which is inland, is the fastest growing metropolitan area in the United States, which puts the strain on our already limited water resources in the state. Moreover, all of these issues are exacerbated by our rapidly changing climate. These days, we regularly withstand harsh droughts, extreme heat, hurricanes, and wildfires. This uptick is extreme weather events is causing water, food, and energy insecurity, which only increases the urgency with which we must act. For these reasons, I have been working for many years in Congress to address this important issue through my work developing the Energy and Water Resource Integration Act. This Congress, I reintroduced that bipartisan bill with my colleague and friend, ranking member of the full committee, Lucas. It instructs the Department of Energy to incorporate the consideration of water use and treatment into all of its relevant research, development, and demonstration programs, and to establish additional coordination functions to ensure that we are giving this issue adequate attention and resources moving forward. I want to thank you, Mr. Lamb, for convening this panel. I'm very pleased to see the strong representation of witnesses, and especially from Texas today. I look forward to having a robust discussion. As I complete my statement, I will say that I do have to attend a subcommittee on water in the Transportation Committee, so I will dip out in a little bit. Thank you, and I yield back.
Thank you, Madam Chairwoman, and the chair now recognizes Ranking Member Lucas for an opening statement.
Thank you, Chairman Lamb, for holding this hearing today, and thank you to our witnesses for being here. There might not be two more important and interconnected pieces in our daily health and economic stability than water and energy. Water is used to produce energy, and energy is required to treat and distribute clean water. Both are essential, and both depend on the other. That's why this Congress, I joined my colleague, Chairwoman Johnson, in introducing H.R. 34, the Energy and Water Research Integration Act, which will be the subject of today's hearing. This bill will improve our understanding of the relationship between water use and energy production while encouraging the development of innovative technologies that could improve efficiency and production in both sectors. It's important to remember that many of the issues surrounding the energy-water nexus are regional and so require consideration of local factors. For example, in Oklahoma, agriculture is clearly a third part of the relationship. While agriculture is the single largest consumer of water, it is also a critical piece of the national economy and contributes indirectly to the energy sector through the production of biofuels. Additionally, oil and gas operations, especially horizontal drilling and hydraulic fracking, which are vital in the pursuit of cleaner energy markets, require large volumes of water and can also produce water. While this presents localized water treatment challenges, it also leads to opportunities for beneficial reuse of water through fluid life cycle management. Today, Raman Singh will provide a valuable perspective from the research community on ways to improve water management and energy efficiency by developing carbon and water neutral fossil energy technologies. I look forward to hearing how his collaborative multi-university effort, led by Oklahoma State, can conduct transformative research while working with industry to safely implement new approaches to the field. This research can also complement the work being conducted at our national labs. I'm pleased to see DOE pursuing work in this area, both through the Multi-Agency Water Security Grand Challenge and the recently announced DOE Energy Water Desalinization Hub. By focusing on early-stage R&D, this hub will work to develop novel filtration membranes that can transform brackish or produced water into water communities can reuse. Because of the complex relationship between energy and water systems, this challenge will require a multidisciplinary approach. Interactions between chemists, engineers, geologists, legislators, and others will be required, along with collaboration between government, industry, and universities. I believe the legislation introduced by Chairwoman Johnson and myself can help to streamline and prioritize this work. I thank our witnesses for being here today, and I look forward to our discussion this morning. And with that, I yield back, Mr. Chairman.
Thank you, sir. If there are members who wish to submit additional opening statements, your statements will be added to the record at this point. Now I'd like to introduce our witnesses. First, we have Dr. Vincent Tidwell, who is a principal member of the technical staff at Sandia National Laboratories. Dr. Tidwell has more than 20 years of experience conducting and managing research on basic and applied projects in water resource management, nuclear and hazardous waste storage and remediation, and collaborative modeling. Currently, he is leading several studies that address issues concerning the energy-water nexus, including support for long-term transmission planning in the Western and Texas interconnections, climate impacts on energy-water relations, and international energy-water pinch points. Dr. Tidwell was a lead author for the Land, Water, Energy cross-sectorial chapter of the 2014 National Climate Assessment. Ms. Kate Zerrenner, did I get that right? Close enough, I'm sorry about that, is a senior manager at the Environmental Defense Fund. Ms. Zerrenner leads EDF's Texas, can you just say it so that I make sure I get it right? Zerrenner, thank you. Ms. Zerrenner leads EDF's Texas and National Energy Water Nexus efforts and develops and implements strategies to promote energy and water efficiency in Texas. Her work aims to address financial, regulatory, and behavioral barriers to advancing clean energy options that reduce climate change impacts, water intensity, and air pollution. Prior to joining EDF, Ms. Zerrenner worked at the U.S. Government Accountability Office, analyzing U.S. action on climate change and the voluntary carbon offset market, SAIC on climate change projects for the U.S. Department of Energy and the U.S. Environmental Protection Agency, and the U.S. Department of Energy. Dr. Richard Bonner is the Vice President of Research and Development of Advanced Cooling Technologies. Dr. Bonner has led research programs involving the thermal and fluid sciences, including several programs related to the energy-water nexus. He has published more than 45 papers, 1 patent, and 4 patent applications. Dr. Bonner has also led advanced thermal project development programs from concept to production for over 125 customers, covering a wide range of commercial industries. We also have Dr. Michael Weber, who is based in Paris, France, where he serves as the Chief Science and Technology Officer at ENGIE, a global energy and infrastructure services company. Dr. Weber is also the Josie Centennial Professor in Energy Resources and Professor of Mechanical Engineering at, you guessed it, the University of Texas at Austin. There's a heavy Texas imprint on our hearing today. Mr. Ranking Member, if I didn't know any better, I would suspect a conspiracy was afoot. But we do have a Pennsylvanian on the panel, so I know we're safe.
Yeah, but he spells his name wrong.
Dr. Weber is the author of Thirst for Power, Energy, Water, and Human Survival, published in 2016. We're guessing he picked up the second B somewhere in Paris, probably, and in that switch to Texas is where it falls off. The chair now recognizes Ranking Member Lucas for the introduction of our final witness.
Thank you, Chairman. It is with great pleasure I introduce one of my constituents as our witness today, Dr. Raman Singh. He holds a number of academic positions, including Associate Dean of Engineering at Oklahoma State, Tulsa, Head of the School of Material Science and Engineering at the College of Engineering, Architecture and Technology at Oklahoma State University, and the Director of the Helmrich Advanced Technology Research Center at OSU-Tulsa campus. His research has been funded by the National Science Foundation, NASA, the Oklahoma Center for Advancement of Science and Technology, the Oklahoma Transportation Commission, the U.S. Army Research Office, the Department of Energy and Industry. And prior to joining OSU, Dr. Singh was a postdoctoral scholar at the California Institute of Technology, a faculty member of the State University of New York at Stony Brook. Dr. Singh holds MS and PhD degrees in mechanical engineering and applied mechanics, both from the University of Rhode Island, and a Bachelor of Technology degree from in mechanical engineering from the Indian Institute of Technology. Thank you, Dr. Singh, for both being at Oklahoma State and being here with us today.
Thank you, Ranking Member. As our witnesses should know, you will each have 5 minutes for your spoken testimony. Your written testimony will be included in the record for the hearing. When you all have completed your spoken testimony, we will begin with questions. Each member will have 5 minutes to question the panel. We will start with Dr. Tidwell.
Chairman Lamb, Ranking Member Weber, and distinguished members of the committee, I thank you for this opportunity to testify here before you this morning on this critical issue of energy and water nexus. Again, my name's Vince Tidwell, and I'm with Sandia National Laboratories. I want to start on a personal note, as I had the opportunity to view the energy-water nexus firsthand. This past week, while I was on vacation, I traveled from Albuquerque, New Mexico to Park City, Utah, and on this trip I crossed the San Juan, the Colorado, and the Green Rivers along with the Rio Grande. I also passed numerous power plants, hydropower dams, oil and gas plays, and coal mines. The relation between these important resources was evident. Equally evident was the critical role these resources play in the economy, livelihood, culture, and environment of the communities that they serve. These resources are our heritage, so thank you for your concern and interest in securing these resources for generations to come. There are 3 points I'd like to make this morning. First is a challenge. The energy-water nexus is expressed in varied ways that often depend on location. Second is an opportunity. We can manage the nexus through integrated planning involving coordinated action between water and energy managers. My third point, again, highlights an opportunity, in this case, to harness the deep expertise of our national laboratories, academia, industry, and other federal agencies to develop advanced water treatment technologies to make new sources of water available at competitive costs. To my first point, place really matters when it comes to the energy-water nexus. For example, in the West, we've had difficulty in siting new power plants due to limited water supply, while in the East, we have had problems in times of drought with existing power plants having to operate differently due not to limited water supply, but because of elevated water temperatures. Drought affects hydropower everywhere, but it's a particular issue in the Northwest where hydropower accounts for over 60% of all generation capacity. On the other end of the spectrum, we see penetration of wind in the Plains states and solar in the Southwest, which has drastically changed and reduced our energy water burden in these regions. This variation simply reflects the geographic differences in our energy, water, and climate systems, underscoring the need for deep understanding of these linkages with broad nationwide participation. To my second point, integrated planning provides an important platform for managing the nexus. As a personal example, I've led a team of researchers, including my colleague, Dr. Weber, to bring state water managers together with energy managers from the nation's 3 interconnections to help integrate water into their long-term transmission planning, specifically identifying where water might limit the siting of new thermoelectric power generation or where drought might impact the operations of existing power plants or hydropower assets. Beyond integrated resource planning, though, we need to integrate waste stream management. Significant quantities of water and energy are required to manage waste, including the emission scrubbers, carbon capture systems, and produced water management. But we don't have to consider these as waste, as new technologies are emerging to extract value from these streams, such as latent heat, biogas, potable water, and commercial chemicals. My final point, again, addresses an opportunity, that of advanced water treatment technology. In 1961, President Kennedy said if we could ever competitively, at a cheap rate, get fresh water from salt water, it would be in the long-range interest of humanity, which would really dwarf any other scientific accomplishment. Today, there are over 18,000 desalination plants in operations around the world, but desalination is still not cheap. Why? The source waters are highly variable. We're also having to deal with other contaminants beyond salt, as we find in our municipal industrial wastewaters, produced water, and agricultural return flows. There's also the confounding issue of concentrate management. That is, what do we do with these salts when we separate them? Toward this need, the DOE has issued a call for an energy water desalination hub, which will invest in early-stage R&D. This provides an unprecedented opportunity to coordinate expertise across federal, academic, and industrial research complex to develop new materials and new processes that will fundamentally change the way we treat water in the future. In conclusion, the energy-water nexus is a complex and nuanced issue. While we are making progress, more work is needed. And I want to stress that we have the opportunity to do more than simply avoid future problems, but rather we can radically change the way our energy systems depend on fresh water while creating new sources of water at competitive prices. Thank you for convening this hearing, and I look forward to your questions.
Thank you, Dr. Tidwell. Ms. Zerrenner?
Thank you. Chairman Lamb, Ranking Member Weber, members of the committee, thank you for inviting me here today. Again, my name is Kate Zerrenner. I'm a Senior Manager of Energy Water Nexus Initiatives at Environmental Defense Fund, Texas office. Our energy choices matter. So coal, natural gas, and nuclear all use vast amounts of water. Solar, PV, wind use negligible amounts. Energy efficiency uses none. And that matters because about 85% of our current energy resources come from nuclear and fossil fuel, and that requires about 133 billion gallons of water per day, or about 41% of total U.S. freshwater withdrawals. And the energy-water nexus is a cascading problem. And with extreme weather, energy-water nexus can quickly turn into energy-water collisions. With climate change, this is intensifying the extremes in our weather. For example, in a drought, water for cooling is more limited, reducing the power needed to move water. Air conditioning spikes during hot and dry days. increasing the demand for power, which increases demand for diminishing the water supply to cool that power system. And this matters because of resilience. So when we're looking at states like mine, like Texas, we suffered a multi-year drought from 2010 to 2015, which was only ended by catastrophic flooding that we endured for 3 years, culminating in Hurricane Harvey. So building resilient systems matters. It matters to make sure that as we see these drought and flood cycles, which we're used to in Texas, but they're getting more extreme. So like an athlete on steroids, climate change may not necessarily be causing these extreme weather events, but they are enhancing their performance. So some of the ways we've addressed this in Texas is we're looking at some specific solutions. 2 legislative sessions ago, you may remember this, Ranking Member, we passed a bill requiring the state to look at using solar and wind to desalinate brackish groundwater on state-owned lands. The study was finished and done by the Weber Energy Group and found nearly 200 cost-effective sites on state-owned lands, which is significant because about 98% of the state of Texas is privately owned. So 194 cost-effective sites for using solar and wind to desalinate brackish groundwater. We've also, EDF has partnered with the Pecan Street Project, which is a nonprofit that looks at energy and water from the smart technology perspective, and we looked at the end user results of what the energy intensity of our water systems and the water intensity of our energy systems in the home are. A lot of people aren't aware of the amount of water they're using when they turn their clothes dryer on, for example. And one of the things we found is that in homes with solar panels, for example, the water footprint of those homes decreased by nearly 80% with solar panels on their homes. So there is a significant impact on our water in terms of how we use our energy and vice versa. The key to all of this is data. That Pecan Street project was the first of its kind to do very granular data collection so that we actually know what we're looking for. We know what we're trying to address. EDF partnered with the Texas Army National Guard to model and map 60 of its 90-plus installations across the 10 climate zones of Texas. And what we did is we took the climate data, in water scarcity, solar potential, wind potential, energy efficiency potential, geothermal potential, and electricity prices, and overlaid all those things together so we could give the Texas Army National Guard the data they needed to invest smartly into what made the most sense in terms of the water scarcity, the solar potential. For example, El Paso came out on top with water scarcity and solar potential, so they can then take that to the appropriators and say, we need to invest in solar in our installations in El Paso, and then they can use money that would otherwise be spent on electricity bills to be spent on things like training and equipment. So there are real-world implications for the choices we make in terms of our water and our energy choices. The federal government has a fantastic role to play here. Data collection, standards, streamlined reporting, all of those things can be done with HR 34 helps to lay that groundwork. In 2011, Chairwoman Johnson requested GAO to do a report on an energy water nexus. I would say an updated report of that nature would be warranted. It has been 8 years. A comprehensive review of both federal programs and funding streams throughout the federal government could help increase the coordination across the federal agencies that work on energy water nexus issues. And with that, I close, and I look forward to any questions. Thank you.
Thank you. Dr. Bonner?
I would first like to thank the committee and its leadership for the opportunity to testify in the Energy Water Nexus. I've worked at Advanced Cooling Technologies, a small business located in Lancaster, Pennsylvania, for over 13 years. The company started in 2003 and has grown to 130 employees. The company was predominantly funded through the government-sponsored research programs in its early days, and today it still relies on government funding for many of its new technology development initiatives. I currently serve as the Vice President of R&D at Advanced Cooling Technologies. I've closely led several research programs related to the Energy Water Nexus while serving as a principal investigator. In the ARPA-E ARID program, I led the development of a technology that could effectively cool power plants using air instead of water. Our technology is analogous to a DVR, but for heat. We demonstrated that you can store cold energy at night and later cool the power plant during the day when the ambient temperature is warm and the electricity demand from the grid is the greatest. Through the Department of Energy's Small Business Innovative Research Program, we have developed non-wetting coatings and surface structures to improve condensation to more effectively remove heat from the steam circulating through power plant steam turbines. In another effort funded through the Department of Energy Fossil Energy Cross-Cutting Research Program, we're developing longer life non-wetting coatings that are capable of being replenished to maintain their cooling effectiveness for decades. Researchers in our R&D group are looking to solve other key water issues as well. Through the Department of Energy's Small Business Innovative Research Program, we are looking at new ways to desalinate water. Through another Department of Energy-funded program, we're developing new ways to collect sunlight to use the energy to directly drive the desalination of brine. Finally, for the U.S. Department of Agriculture, we're looking at ways to desalinate brackish water and use the water to directly feed the roots of plants by using a system of underground plumbing. This innovation may make it possible for the agricultural industry to tap into the vast amounts of brackish water available, which will free up freshwater supplies for other critical applications. Recently, I was invited by the Arizona Public Service Company to tour the Palo Verde generating station. Palo Verde is the nation's largest net power generating station. The nuclear power plant is located in the desert regions of Arizona, not near any bodies of water, which makes it unique. Their current water solution is quite interesting. The power plant water is completely supplied by treated sewage that is purchased from several local large municipalities. However, the demands on this water supply are causing the municipalities to increase the price of this precious water supply, which will ultimately lead to an increase in the cost of power for the region. I met with their senior engineering team to present some of the water reduction cooling solutions that we have developed, and we hope to begin working with them in the next few months. Without the substantial funding and experience gained through the numerous government-sponsored research programs that I mentioned, we would not be talking with the Arizona Public Service Company to solve their water and cooling problems. The government-sponsored funds are critical to small businesses such as ours, so we can take our ideas and mature them to the levels demanded by the marketplace. Finally, I would like to discuss some recommendations to the committee about some legislative features that would help industry better solve the energy-water nexus problem. I want to first remind and impress upon the committee with the scale with which power plants operate. It is simply massive. Further, power plants are not built every day. As a matter of fact, they're not built often at all in the United States anymore. This makes the often mentioned R&D valley of death that much more deadly for companies, universities, and national labs as they try to commercialize their research in this area. So how do you go from the benchtop in a lab to a power plant-sized systems, and how can the government help? I suggest that any legislation in this area should aim to address these questions by allotting some portion of the funding for scale-up and subscale demonstrations, perhaps as a follow-on for successful programs. I've seen this follow-on type of program work very well in the SBIR programs, and I could see something similar for some of your other funded efforts. I also want to discuss the cost share requirements that have been common for many of the Department of Energy funded programs as of late. Given the difficulties of scaling up and the large follow-on investment that is required by companies to reach utility scales, the R&D cost share requirements seem to unnecessarily hinder industry's flexibility to use financial resources where they are needed most. I recommend that the cost share be eliminated or at the very least changed to allow the companies to get their cost share credit through non-R&D based investments. These alternative investments could include capital spending on related production equipment, intellectual property protection, or perhaps sales and marketing. It has been my privilege to testify in front of you today. Thank you again for the opportunity. I look forward to answering any of your questions.
Thank you. Dr. Singh.
Good morning. It's my honor and privilege to be here. I'm the head of the School of Material Science and Engineering at Oklahoma State University, and I also direct the Helmerich Research Center. I do have to apologize, I'm not a native Oklahoman, but in my own defense, I got to Oklahoma as soon as I could, and I've managed to raise 2 daughters in Tulsa, and they will both end up going to college in Oklahoma right now. I'm leading and building a consortium of multiple universities led by Oklahoma State, involving Caltech, the University of Utah, Northeastern State University, and the University of Tulsa, along with several industry partners and Sandia, to look at the safety and sustainability of fossil fuel production and consumption. And it is with regards to that I'm going to talk about the produced water and the water issue today, which is only one aspect of what we are looking for in our consortium. My perspective is that the prosperity of any nation, prosperity of our nation, ultimately depends on our ability to safely and sustainably produce and consume energy. And the bulk of our energy today, even though you don't realize it, comes from fossil fuels. There will be a future where we will displace these fossil fuels with renewables, but there has to be a bridge. And the way we see technology today, this bridge primarily comes from natural gas produced through hydraulic fracturing. It's a significant resource that we have. It's the cleanest burning fossil fuel with the least impact on greenhouse gas production. But this is where water comes in, because you require water to essentially break rock in terms of hydraulic fracturing. You require large amounts of water, and more often than not, this water is fresh water. And then the process itself produces water, which is known as produced water, which is stuff that comes out of the ground along with the production of shale oil and shale gas, and it is highly contaminated. It carries a lot of salt, and by itself, dealing with produced water has led to other engineering challenges by itself. There are three areas of technology that I want to focus on. The first one is the hydraulic fracturing process itself. I think there are significant opportunities in trying to minimize the amount of fresh water that's used in this process, and at the same time increasing the efficiency in which we are able to recover materials. Right now, the recovery rates are typically 10 to 20%. So and this is where all the projections are made. So we are recovering only about a tenth of what is possible in terms of shale oil and shale gas. There is some research that has gone on. The way I look at it is water is not the only way to break rock. It's a good way, and it's a simple way, but there are other ways which involve comminution of rocks, and this is a research area that I've been focused on. The other aspect is, what do you do with the produced water that comes out? Now, electrical or solar desalination of produced water is expensive. It's very highly energy dense. But the idea that we're looking at is that we want to try and get it clean enough to drink. We don't have to get it clean enough to drink. We have to get it clean enough so that we can use it for something else and look upon it as a resource rather than a waste that needs to be disposed. There are a lot of membrane filtration technologies based on ceramic nanoporous membranes that are being pursued. This is some work that we're doing at Oklahoma State. And the idea is that you get it to the point where the number of total dissolved solids, that's how you track how contaminated the water is down to a point where you could perhaps use it for industrial processes, you could use it for agriculture or rangelands without trying to get it clean enough to drink. And the other resource that is fairly interesting from the perspective of produced water is being able to extract chemicals from it. I'll give you an example, lithium. The demand for lithium has been growing tremendously. It'll continue to grow as we move more towards an electrical-based economy simply because of battery storage requirements. We import all of our lithium today. If we were to be able to extract 50% of the lithium that comes out in produced water, we would become a net exporter of lithium without introducing any other mining operations as far as lithium is concerned. And that's just one example of what can be pulled out. Unfortunately, the problem is very complex. I mean, I'm an engineer. I like to think like an engineer. I like to believe that all problems in the last 100 years have been caused by engineers, and all solutions came by engineers too, right? So, but a problem like this requires a nexus between engineers, legislators, regulators, industry, academia, and so forth. And that's where I think this committee can play a tremendous role in terms of setting the tone in the direction we need to go forward. So, it's been an honor and a privilege for me to be here, and I would be welcome in taking any questions. Thank you.
Thank you, Dr. Singh. I'm glad you said that, because the next time I go home and someone tells me that the politicians in Washington are screwing everything up in this country, I'm going to say, no, I have it on very good authority. It's the engineers. So, Dr. Weber, go ahead.
Thank you very much, Chairman Lamb and Ranking Member Weber. I appreciate the opportunity to submit testimony today. As you have heard, the energy-water nexus presents unique challenges and invites cross-cutting solutions. Because the energy system depends so extensively on water and the water system depends so extensively on energy, they are both vulnerable to cascading failures from one sector to another. For example, a water constraint can become an energy constraint, and an energy constraint can become a water constraint. If water is not available at the right place and time with the right quantity and quality, then the power sector might struggle to generate and deliver electricity. And if energy is not available because of blackouts, then the water sector struggles to treat and deliver water. That means the energy-water nexus is a resilience challenge for planners. Thankfully, it also invites cross-cutting solutions, especially for conservation and efficiency, namely in saving water saves energy and saving energy saves water, which avoids environmental impact and improves resilience. For my remarks, I will focus on two aspects: the energy use for the water system and specific challenges related to managing wastewater from oil and gas production, building on Dr. Singh's comments. The combined water and wastewater system is a hallmark of a modern society, and because the economic and public health benefits are so extensive, they are the most important public investments a society can make. These water and wastewater systems also require vast sums of energy for pumps, blowers, chemicals, and mechanical equipment. We use more energy in our buildings to heat water, and then industry uses even more energy to treat that water further, for example, to make ultra-pure water for semiconductor fabrication or to make steam for use in refineries. All told, about 13% of national energy consumption is for direct water and steam services. About 1/3 of that, or about 4% of national energy consumption, is just to heat water in our homes and businesses. That is about twice the amount of energy that Sweden uses to run their entire country. So we use a lot of energy just in heating the water. As a result, water heating represents an opportunity for saving energy and avoiding emissions. In most parts of the United States, shifting from electric heating towards natural gas heating or solar water heating reduces energy use and CO2 emissions. And if we clean the grid up, similar to what we have in the Pacific Northwest, that's mostly hydro, then electric water heating would be an excellent option as well. Incentives and information guides to encourage adoption of more efficient appliances that use heated water, like dishwashers and clothes washers, would continue to provide non-trivial savings. According to one study, the average U.S. household could save hundreds of dollars on their electricity and water bills by making those appliance upgrades with the types of upgrades that pay for themselves, meaning they save money in addition to reducing consumption. In addition, wisely managing the end uses of water and energy would improve the resilience and efficiency of military installations, which makes this a national security issue also. The water sector's energy needs can also be used to integrate higher fractions of renewables into the power sector. Water treatment, wastewater treatment, and modern desalination plants that use reverse osmosis are particularly electricity dependent. They can be ramped up and down and operate flexibly, which makes them a good companion for variable resources like wind and solar. Furthermore, it is much easier and cheaper to store water than to store electricity. For example, you can use simple water tanks to store water instead of expensive batteries. And that means integrating renewables with the water sector can help make the electricity sector more resilient while providing valuable grid services and speeding the adoption of clean forms of power. Another issue, as you heard, is the amount of wastewater produced alongside oil and gas extraction. Unfortunately, water and wastewater are often moved by trucks, which are less efficient, dirtier, more disruptive to communities, and more destructive to roads than pipelines. Building a pipeline-based wastewater collection system would improve the safety and impose much less environmental risk compared with truck-based movement. Such a system would also reduce the cost for oil and gas production, helping propagate the ongoing boom in places like West Texas. A water pipeline network would also enable specialized capabilities with economies of scales for treating this very dirty water, which would open up the case for water recycling and reuse while avoiding disposal by underground injection. The federal government can help. Uncertainty about gaining right-of-ways on federal lands make it harder for developers to build these wastewater collection networks, which inhibits the construction of treatment and recycling systems, leaving underground disposal as a primary wastewater management option and putting pressure on aquifers. Facilitating pipeline construction would help accelerate the adoption of better management pathways. In addition, policy stability and certainty is important for developers making decisions to invest in long-lived assets. Policy shifts from year to year and government shutdowns increase those costs and delay the projects that have environmental benefit. A couple closing comments is that in addition to facilitating the development of water collection networks, the federal government has other actions it can take. Encouraging the Department of Energy to have water in mind for its programs is a good place to start. Encouraging water planners to keep energy in mind is also important. In addition, data collection and sharing programs can make a big difference. Data on urban water use is particularly scarce in comparison with our energy data, which makes it harder to manage usage or improve resilience. The EIA data sets set the gold standard for energy data, and we need something similar for water, perhaps by creating an agency with that task or by expanding the EIA's mandate to include tracking of water demand and supply. Lastly, one of the most important policy levers for the federal government is to sponsor R&D. Incremental improvements will not solve these challenges quickly enough, so there's a need to scale up the effort. The U.S. innovation system is the best in the world, so it makes sense to leverage those strengths to our advantage. Thank you for the opportunity to share my thoughts. I'd be happy to answer any questions.
Thank you. We will now begin our round of questions, and the chair recognizes himself for 5 minutes. Dr. Tidwell, I wanted to ask you, many people have identified how water issues vary across the country, especially as climate change gets worse and worse and becomes more apparent. I can give you a local example. You know, I know you've talked about out west, there's often droughts and a water shortage. In western Pennsylvania, where I live, the problem is often too much water. We're having very intense and more frequent rainstorms. We have a very hilly area. And interestingly, someone told me there's roughly 5,000 water systems in the United States, the continental United States, for treatment and drinking water. About 1,000 of them exist in the 10 counties of southwestern Pennsylvania. It's an interesting historical legacy. It makes it very hard to coordinate our efforts when it comes to water treatment. So I was curious if you could just give us a very brief insight on how we can help to encourage the regional cooperation that's necessary in these different areas.
Thank you, Chairman, for that question. Certainly, I think one of the low-hanging fruits that we have for this energy water nexus is this very problem of integrated planning and bringing different groups together. Certainly, the opportunities that we face with these small systems, there are rural water industrial groups that help these systems and to provide them with the tools that they can then use and work with their local constituents, I think would be one important place. Another important place as we go forward is going to be in the development of workforce skills, as many of these smaller areas are not able to employ folks with the necessary skills. And so going forward, we're going to need to develop a trained workforce as some of these more complex technologies come in place to treat water, to manage our water systems and our wastewater systems. So I think
that's a fantastic point. Thank you very much. Dr. Weber, I wanted to ask you about the pipelines for hydraulic fracturing wastewater, big issue in Western Pennsylvania where we're doing a lot of hydraulic fracturing. I'm not familiar with pipelines being constructed near where we live for the actual wastewater. Most of it is being trucked out, and it does cause a lot of impact on the local communities. Are there areas where they have successfully built a pipeline network for this?
This is a good point. Water and wastewater is primarily moved by trucks, and the trucks are a source of discontent with a lot of the communities because they change the rural lifestyle. They add a lot of noise, a lot of dust. They lead to traffic accidents and deaths and road impact. Pipelines generally are much more expensive to build, but much safer and cheaper to operate once you have them built. And there are some nascent water and wastewater collection systems out in New Mexico and West Texas primarily, maybe a little bit in the Bakken Shale, North Dakota as well. So there are some examples where you have concentrated production of oil and gas, and you have a policy-making process where it's easier to build, and the land is also flatter and easier to build on, say, than the Appalachian Mountains, other places. It's easier to build, and then that reduces the cost for sourcing the water, collecting the water, treating the wastewater, that kind of thing. So there are some examples. When I talk to oil and gas operators, I think they'd like to see more water and wastewater systems built because it would reduce costs and do less damage.
Do we have any policy levers at our disposal on the federal level to try to encourage that in an area like mine that is topographically a little bit different than the Southwest?
I think a lot of these decisions are made at the local level or the state level, so often it's the state level policymakers, but there are some federal levers at play whenever you're on federal lands, for example. As you get further west, you get to BLM lands, for example, and then the federal levers become much more important. Most of it's at state level decision making, but there's a role for the federal government to play in convening the state level policymakers and sharing data and information that they can't collect themselves. So I think there is a role for the federal government, but it requires cooperation at the local and state level as well.
Thank you very much. And last question, very quickly, Dr. Singh, you mentioned alternatives to water for hydraulic fracturing, just in sort of 10 seconds or less. Are we close on any other fluids besides water, or I guess non-fluid solutions?
Turn your mic on, please.
I think water will continue to be the major driving fluid, but the amount of water that's used can be cut down a lot. And plus, some of the produced water can be recycled and used back at the source itself for that. Does that answer your question?
It does. Thank you very much. I now recognize Mr. Weber for 5 minutes.
Thank you, Mr. Chairman. I'm going to give you something to read here about purple pipe. Very quickly, Dr. Tidwell, have you ever heard of purple pipe?
Yes, sir, I have.
Ms. Zerrenner, is that right? Right that it's right, or right that you've heard about pipe?
Both.
Okay, good. Dr. Bonner?
I haven't heard about it.
Dr. Singh?
No, I haven't.
Dr. Weber?
Yes, and I've written extensively about it and done research on purple pipe.
Really? Okay. you know, that it's a system that takes from a home or a business. It's not necessarily wastewater from the toilet, for example, but it may be from the sink or dishes or whatever. And it treats it to the extent that it doesn't have to be drinkable, but it could be used for irrigation and other things like that. And I thought perhaps that might be part of y'all's focus today, but we'll go in there later. Now, I'm from Texas, as Dr. Weber knows, and I often say that any state worth its salt has a desalination plant. And some of y'all get that on the way home. And we have one in Texas. Back in my days in the Texas State Legislature, I had the opportunity to tour a large-scale desalination plant in Brownsville. Have any of y'all been to that plant? She has, but y'all haven't. Ladies are always leading the way. Have y'all noticed that, gentlemen? It's okay to say yes. Okay. I'm going to get y'all softened up here. I've seen firsthand the amount of electricity required to convert brackish water to potable water. Dr. Singh and Dr. Tidwell, as you know, DOE recently announced $100 million in funding for an energy water desalination hub that we talked about, focused on early stage research and development to explore those uses for non-traditional water sources and to develop new desalination technologies. So a couple of questions for you, and I'll start with you, Dr. Tidwell. Will the research funded by this hub focus on reducing the energy necessary to be used in those current desalination plants? Your thoughts?
Yes, sir, that's a good question. And yes, I think there are opportunities to help with existing plants. One would be, one example would be with improved membrane technology that would help reduce fouling. So that would be one example where
so the product, the output, the product would be cleaner, easier. But do you know what the #1 energy driver is in a desal plant, or need is in a desal plant?
it's the pressurization of the water.
It's the pumps.
Pump.
The pumps there in Brownsville, and I'm going back now 10 years, must have been this big around.
Yes, sir.
And the electricity required to drive those is really tremendous.
Which is forcing the water through those
Correct.
membranes. So anything that can help improve that permeability
Right.
would
Improves
help
the
reduce the
efficiency, get more water out a little cheaper.
Yes, sir.
Because they're bringing water, and I think it was a 12-inch pipe. Now I'm going from memory, from the Gulf of Mexico into Brownsville, and the distance they have to bring requires a lot of electricity and a lot of pumps. Do you agree with that, Dr. Singh, that focus will be on increasing efficiency?
Yes, I agree, because conventional desalination requires, it's very energy intensive.
Yeah.
The only reason you would do that is if you had no other source of potable water. There are technologies based on electrocoagulation, which can clean up what's going in before the membranes kick in. There are technologies using ceramic membranes, which can increase the efficiency, but that efficiency will need to go up.
Right. And of course, that's going to depend, let's face it, on the cost of electricity, right? And so I think we could all agree that the lower the price of natural gas is, the cheaper that energy companies can produce energy, that in and of itself will have a reduction in the cost of desalination. Would you all agree with that? Mm-hmm. Absolutely, you betcha. So fracking is a good thing. I'm glad we all agree on that. In your opinion, Dr. Tidwell, what impact could this hub have on your research? What would your role be?
Most of my work is around modeling and analysis, and so importantly, understanding how climate change affects the resilience of our energy water systems and integrating uncertainty in those changing climate, changing demands for water, changing technology, and how we can plan for a robust, resilient system going forward into the future.
How about you, Dr. Singh? Your research, how would you correlate this, correspond? How would this impact you?
2 areas of research. One would be increasing efficiency of basically breaking up rock to increase extraction efficiencies, not only for fracking, but also for geothermal systems. And the second aspect would be, which we haven't talked about today, would be reducing the mitigation due to induced seismicity or reinjection. So these are the 2 areas that would be affected the most.
Okay. Thank you, Mr. Chairman. I yield back.
Thank you. Now recognize Ms. Horn for 5 minutes.
Good morning. Thank you all for your testimony. And Dr. Singh, as a fellow Okie, it's good to see you here today. So I have a couple of lines of questioning, and I want to start with you because I think you brought up a couple of important points. As I'm sure it comes as no surprise to anyone, both water and energy are big issues in my home state as well as that of the ranking member of the full committee. So I wanted to follow up on some of the points that you made about the need for interdisciplinary work, because part of the challenge with fracking is, and the challenges that we've seen in Oklahoma with earthquakes and things like that, comes from the wastewater reinjection more so than just the breaking up of the rock itself. So I wanted to see if in your research you had looked at the impact that might have of taking the water, and in addition to taking it out and reusing it, the impact in other areas for energy production.
I don't understand the other areas part, but I can talk a little bit about the reinjection. Reinjection right now is not very well understood. I mean, the way we have a traffic light system in which if they feel that there is something that's going to happen, reinjection stops. And this reinjection problem is not necessarily a problem that's limited to fracking. Induced seismicity also happens in geothermal fields, in some geothermal fields in Europe, in technology, energy production technology that is quote unquote much greener than fracking. There were initially some concerns in terms of how clean does the produced water need to be for it to be reused for fracking, but that concern is not because of reinjection. That concern is mainly from being able to control the chemistry to allow the fracking process to be more efficient.
And if the technology continues to develop to take the wastewater from the fracking process to be more usable, potable, even if it's not drinkable, what impact does that have on the amount of reinjection that would have to occur?
So to give you some numbers, a fracking operation at a well in its lifetime will take about 2 to 8 million gallons of water. We produce about 60 times produced water every day than that's used in the city of Washington, D.C. So some of it will go back as for reinjection, but that's not the only solution. The other solution also has to be to look upon produced water as a resource, to use it for other purposes. And in Oklahoma, that, for example, could be agriculture or rangelands, and not necessarily cleaning it up all the way for human consumption.
Thank you. The second area, and I'm going to open this up because I think it may be best for Dr. Tidwell, but if anyone else has thoughts on this. In Oklahoma, in addition to the municipal, state, and other federal issues, we have 39 tribes, federally recognized tribes in the state of Oklahoma. So this energy water nexus also impacts issues surrounding tribal sovereignty and water usage and water rights. So I'm wondering if you could talk more about policy recommendations or areas that you see emerging with this federal, state, local, tribal lands issue.
Thank you, Congresswoman. This is a very important issue. I think at the end of the day, what it really boils down to is improved communication across all of these different entities. One of the important aspects of particularly the Indian water rights is that in many cases in the West, they hold rights or their rights haven't been fully adjudicated. So they play a very important role in how future water might play out in many cases in the western United States. And so they are an important player that we need to bring to the table, as well as the states. The states ultimately have jurisdiction over their water. I might mention that DOE also has numerous programs for helping to support energy development on Native American land. So all of these particular activities need to be coordinated, and integrated planning is a very important part of all of that.
Thank you. Mr. Chairman, I yield back.
Thank you, and recognize Ranking Member Lucas for 5 minutes.
Thank you, Mr. Chairman. As I mentioned in my opening statement, there's an abundance of natural gas resources in my district and in many parts of the great state of Oklahoma, as we've discussed. But also as a farmer, I understand and appreciate the importance of the reliability of water, and I'm particularly interested in the research partnerships and results in these areas. So I turn to you, Dr. Singh. In your testimony, you expressed the same sentiment, but by saying meaningful interactions are needed across a variety of stakeholders, including universities, local governments, and industry. Can you give us some examples of that collaboration that you and/or Oklahoma State and industry stakeholders have been a part of that's generated beneficial results?
I'll give you one small example, and this came about our discussion with One Oak. Now, One Oak transports a lot of natural gas that's produced. In the winter, to transport this natural gas across pipelines, they have to add methanol to as an antifreeze, basically. Now, at the same plant, they're flaring methane and burning it burning it away. So one technology that came about, and this is research now that's been done, and this actually involves partnership with a very eminent chemist at Caltech, is to take the on-site methane, convert it into methanol, use that methanol instead of pumping methanol to the stations and then discarding it at the other end. The only reason this came about was because I was in discussion with the One Oak researcher and talking about issues. And this is a very specific example, I understand. But I think in terms of my perspective at the Helmer Research Center, a lot of this discussion has been driven by industrial advisory boards in identifying the problems that academia can solve.
So let's touch on that for just a moment, the industrial advisory boards. Your experiences with the interaction, and are there ways that perhaps we could help encourage that collaboration?
Yes, I think for us, especially as academia, when we seek out, let's say, federal or state level funding, when that funding specifically mandates convergence type of research or, talking to various stakeholders in terms of the probability of getting funded, then that pushes multiple people to the table, and that has been helpful in our case.
I can't help but, Dr. Singh, touch for a moment on the topic of fracking and injection wells, which is a very sensitive subject in our great state of Oklahoma. In my home area, typically the oil and gas products come out in the particular area I'm at, and it varies, of course, in the 10, 12, 13,000 foot range. And historically, fracking has gone on in my home area at least since the early 1970s. Not as aggressive as the hydraulic fracking, the improved technology, but fracking's gone on. We've never had earthquakes or that sort of stuff. The injection well process that's come along in recent years, where again, typically in my area, the material comes out at 12, 13,000 feet, but it goes back into an injection well at 5,000 feet or so. We seem to have a different kind of a lubricating zone there, so to speak, under the earth. But wouldn't you agree that the Oklahoma Corporation Commission, the entity with primary jurisdiction in our state, has been very aggressive in how they've responded to these issues about the seismic issues that have come from it, how they put limitations on certain areas and this and that and the other?
Yes, and I think a lot of that comes from a lack of scientific understanding as to exactly what goes on. I think it's a problem that can be managed. A similar analog would be to say all fossil fuels are bad and stop consuming them tomorrow, which means we would come to a standstill as a country. So
exactly. Therefore, it's fair to say that the Oklahoma Corporation Commission is trying to respond in a way until technology can catch up, until we can do the things we need to do to be able to address this process. Thank you, Doctor, for being here today. And with that, Mr. Chairman, I yield back.
Thank you, Mr. Lucas. Who's next? Recognize Mr. Caston for 5 minutes.
Thank you, Mr. Lamb. Thank you to the panel. Dr. Weber, you had mentioned in your written testimony about creating sort of an energy information administration for water. I'm an energy geek. I love EIA. I think it's a great idea. I should mention by way of background, in my prior life, I ran a number of clean energy companies where we went into industrials, tightened up their energy envelope, and among other things, ended up running all of the energy and water assets at Kodak Park in Rochester. It had a 50 million gallon a day water intake permit. It was kind of a cool job for a 12-year-old boy inside me. I mention that because energy metering is pretty robust because at every point in the energy system, people pay for things. There are revenue meters, buyers and sellers want accuracy. Water metering is terrible. The internal metering is shoddy. They're not calibrated very often, often doesn't exist. And it's basically a problem that the water's too cheap, that it's not worth the time to meter. If we were to create a water information administration, I'd like your sense, number one, of realistically, how many meters do we need to put in? And because to my mind, it's a metering problem first. And number two, as you look at water data, where are you skeptical given the meter gaps? Because in my experience, you got to put plus or minus 20, 30% error bars on a lot of the water data you see.
That's a great question, great context. I think the water metering world lags behind the energy metering world, and the water data world lags behind the energy data world. Energy typically is more expensive. It's also more central to other economic and national security aspects. But frankly, if we go back 50 years, the energy data was pretty bad too. It wasn't until the 70s and the energy crises that we created the EIA to start tracking it more closely, because there was a sense of urgency and importance to it. And then once we started tracking data with more fidelity on place and time, so we tracked it daily, weekly with prices, total consumption by fuel and by location, by industry and sector, then we could spot opportunities for efficiency and savings. When we get to that level of data, I think for water, we can spot other opportunities, but when water's too cheap or we don't feel a sense of urgency, it's hard to do that. I think in the specifics of the question of metering, we have about 100 million households. We probably need a smart water meter for every household, so maybe 100 million smart water meters. Plus, we need them throughout the distribution networks because 10 to 40% of treated municipal water is lost from when it leaves the plant to arrives at the home, which means we also need meters throughout these distribution networks to track those losses so we can get repairs done quickly and avoid all that lost water and all the energy embedded in it. So there's a lot of opportunity for data platforms, smarter meters, better meters. Right now the meters are not very smart, or they're read by hand, or they have these errors, or they're not metered at all in some cities in the United States. So this is a big opportunity, and the EIA lays the blueprint for how to do it if you had a WIA, for example.
Related, and anyone in the panel has got a thought on this, you've layered on top of that we have fairly good, subject to everything we just said, fairly good data for surface water. And some reasonable concern about falling snowmelt. I think on a per decade basis, since 1967, we're losing about 11% of our snowpack every decade rather. The data on groundwater is a lot worse. And, there's been places in Northern California that I'm aware of where the water coming out of aquifers is now exceeding the salinity levels that they can land apply. Which, this is beyond Thunderdome kind of territory. How confident are you that we have good data on the water, the sort of the prehistoric water, if you will, and what should we be doing as a government to make sure we have a good handle on that?
Yeah, the fossil water, some people call it. So we have much better view of the surface water. We can see it, we can measure it. The below ground water we don't see as well. We don't have great metering systems in most places, so we wait until the well goes dry or the well goes salty, and then we know there's a problem. NASA is a big partner for this because they can measure water content of aquifers from space more readily than we can from the ground, ironically. So there's partnerships with the national labs, with NASA and the agencies. I think ramping up on just a water tracking system would be useful because then everyone can make decisions and planners can make better informed decisions about where to put their capital based on where the water problems are.
Okay. Last question with a little bit of time I got left for Ms. Zerrenner, if I'm saying your name right there. You had mentioned how much water the nuclear and fossil fuel industry uses, and I used to tell people all the time, if you want to understand the problems with our fuel system, with our energy system, draw a power plant, and everybody draws a cooling tower. However, that's really specific to the open loop systems. Do you have any estimate of how much of our fossil nuclear sector is closed loop, and what we might be able to do to encourage more closed loop water systems on the fossil side?
Yeah, Michael may know the exact numbers. I don't know the exact numbers, but we're seeing more and more movement in that direction. So we see an average of the amount used by coal and nuclear and natural gas because of the differences and the different types of cooling. You have also, besides closed loop and open loop, you also have dry cooling and wet cooling. And the dry cooling they use a lot more water, or use a lot less water, but they also are less efficient. So you have some trade-offs there. So you're creating some issues around that. But really, we want to see more energy efficiency, which uses no water. If we make our systems more efficient, they are also more resilient. We saw other issues like during Hurricane Harvey where the wind turbines continued to turn in the Gulf of Mexico, but the grid was down, so they didn't have anything to connect to. So thinking in terms of microgrid systems and making those more efficient as well, there are lots of moving pieces to this, but I don't have the exact number of the system.
Well, I'm out of time, but just make a plug for cogeneration while we're out here, because so much of that's what we did in Rochester, and the fact that George Eastman built a power plant in 1880 that's twice as efficient as the U.S. power grid today is a lesson I think we can all learn from. Thank you. I yield back.
Recognize Mr. Biggs for 5 minutes.
Thanks, Mr. Chairman. I thank all the members of the panel for being here today. Dr. Bonner, I was interested in your paragraph in your written statement and then your testimony with regard to Palo Verde Nuclear Generating Station in Tonopah. And you were just there recently?
Yeah, I was in the last month, yeah.
Yeah, well, see, so you were there during the good weather time, so good for you. Hope you get out there in the summer and experience what real heat's about. So you mentioned in your statement that there's competing demand for the water, and we're talking effluent, I assume.
Yes.
Okay, and so I think I know what they are, but maybe you want to elaborate on what some of those competing demands, because the Tonopah's, most people don't know this, where Palo Verde Generating Station is in a remote part of Maricopa County. Maricopa County Arizona's got 7 million people in it. Maricopa County has 5 million people in Maricopa County. It's an odd state. We only have 15 counties, and where you went is really remote. There's no water supply, as you mentioned. But what are the competing demands for effluent in basically an urban area that has 5 million people in it?
Right. I think part of the water is to go back to the town for its own purposes. But I think the copper industry also uses a lot of water as well in that area. And other industries, it's a very, it's a growing area. There's a lot of, I think, retirement homes and stuff being put up there too, people moving there. And that demand is just causing more needs on the water. And I think a lot of the contracts that were negotiated for that water when the plant were built were 30 years ago. And I think the municipalities are under the impression that they gave it away too cheaply, especially now with how the local area is growing, and they're trying to get more out of it.
Yeah. You didn't mention golf courses, but there's a lot of golf courses in the valley.
Yeah, that's with the retirement part.
Yeah. So as we take a look at that and the demands, you indicated that you were working on ways to mitigate either the cooling cost or what exactly. I'm not sure what you were working on, but I assume that you're trying to find a way to lower costs either by reduction in use of the effluent or some other cooling mechanism. So can you elaborate on that for us?
Sure. So Palo Verde uses wet cooling towers, right? So all the water, or at least 95% of it, goes to evaporation, and the rest of it goes to evaporation ponds. So our concept would, in order to get rid of water usage, would be use some sort of dry cooling technologies. And we were at an air-cooled condenser users group a few months ago. That's where we sort of made the first connection. They saw some of our concepts that we developed on the RPE ARID program, where we can use salts to essentially store heat at night, and then during peak demand, when it's hot at 3 o'clock in the afternoon, you can dissipate the heat to that basically nighttime temperature, but dissipate it during the day. And by doing that, you can use no water, but you can also get temperatures that are similar to what you get in a wet cooling tower. So you don't have the efficiency issues that Mr. Zerrenner was talking about. If you try, especially in somewhere like Arizona, to dissipate directly to air, usually you're talking about at least a 15% decrease in power efficiency. And I suspect in Arizona, even to reach that, you're talking about a very, very large air-cooled condenser system using traditional technologies that would be not even close to cost competitive to what they currently do.
So I guess that leads me to the logical next question is, what would it cost to retrofit to something that's air-cooled? I'm not asking for a bid. I'm just, a ballpark.
Right. I think it's, when I was there talking with them, and we were in the room with some other air-cooled condenser companies, I think you're talking about at least 10 times more expensive than a wet cooling tower in terms of capital cost. So it's substantial.
But does it offset over time with the usage cost, with the rising cost of effluent?
It probably would, yeah, it would offset over time. But I think
That's the salesman in you saying that, right?
Yeah, a little bit. Yeah, but the paybacks are longer than what the stakeholders want to see.
Right, okay. Thank you very much. I'll yield back.
Thank you. Recognize Mr. McNerney for 5 minutes.
Well, I thank the chair. I thank the witnesses. Very interesting. I've got a lot of questions, and they're not really mean questions either, so I look forward to your answers. Dr. Bonner, as water becomes scarcer in the west and southwest, I really liked hearing about the alternative cooling techniques for the Palo Verde nuclear generation statement. How would that work? I mean, how would the technology you're talking about reduce water consumption at a nuclear plant?
Right, so again, overall, for dry cooling, you're dissipating heat to air. So it doesn't use any water at all, right? You're not going to be taking any fresh water and evaporating it. So it's similar to how most air conditioners would be cooled or most electronics would be cooled. The heat eventually sinks to air.
So it's basically what the prior question was.
It's very similar.
Okay,
to that, yeah.
Thank you. Dr. Weber, in your testimony, you recommended a scale-up effort of the R&D in the field of water energy nexus. I've proposed a piece of legislation last Congress that put a lot of effort into that issue. Could you elaborate on what you envision for a scaled-up effort?
Yeah, thank you for your support of R&D, and I think there's an opportunity for more. If you look at the scale of the problem for the energy sector, which is a multi-trillion-dollar sector around the world, the few billions of dollars a year we spend on federal R&D seems very small by comparison. And then if you look at water, it's even more stark because we spend less than $1 billion a year on water research, and that includes a lot of the environmental water quality issues. So I think there's an opportunity for many more investments to be made in better water treatment systems, the membranes that Dr. Tidwell mentioned earlier, better pumps that were called out earlier from the desalination systems, variable speed drive pumps. There could be all sorts of work into the chemistry. There's a variety of things we can do to look at the water side and reducing the energy intensity of water, but also, as Dr. Bonner mentioned, looking at the water intensity of energy and coming up with new materials or heat exchanger designs or cooling systems for the power sector, as well as looking new techniques to reduce the water intensity of oil and gas production. There's a lot of opportunity for R&D. It's something that industry has stepped away from over the last few decades. The industry looks really more at applied R&D rather than basic R&D or fundamental science. So there's room for the federal government to fill that gap, and industry has been calling for it along with academics and national labs. So I think just the level of funding and the sense of urgency around it has room for stepping up.
Great. I was kind of intrigued by your statement that water is cheaper to store than energy. So do you see a practical way of using that to store energy or to use energy water more efficiently?
Yes, so there are a couple examples. I'll take the water heating example. There's a lot of electricity that goes into water heating. A lot of our water heaters are on around the clock, whether we need them or not. And so we could turn off water heaters if we need to save power. And turning off the water heaters is the same as discharging power from a battery. It has the same effect on the grid. In France, they have a peak demand that's 1/10 of what the United States has. They have a peak demand of 100 gigawatts of electrical power. In the United States, we have 1,000 gigawatts. In France, they can turn off 3 gigawatts worth of electric water heaters to save 3 gigawatts or 3 nuclear power plants worth of power for the grid. That's about the same as having a lot of batteries do the same thing, but it's a lot cheaper to turn off a water heater than, say, turn on a battery. We could do the same thing in the United States, where we use water systems in a flexible way, turn them on and off, ramp them up and down, to achieve the same benefits for the grid that a battery might do, but it's a lot cheaper to turn something on and off than build, buy, install, and operate a battery.
Well, I'm just thinking more in terms of desal, or you can use electricity to desal and store that.
Yep.
And use it rather than, so that's a really good match for renewables, which are intermittent.
Absolutely. So you can ramp desalination up and down. You can ramp water treatment and wastewater treatment up and down, and ramp them up and down to match when the renewables are available. In that case, the water system can help speed up the adoption of those renewables.
Mr. Chairman, I don't know how much time I have, so I'm going to continue to talk until you stop me, but I don't think I'm running out of time yet.
Go for it.
All right, thanks. Dr. Singh, you mentioned that hydraulic fracturing is essentially the cleanest, but the problem in my mind is that just a small amount of natural gas fugitive emissions cause natural gas to be dirty compared to other forms of fossil fuel. Can you address that?
Yes, that's correct. So natural gas of all fossil fuels is probably the cleanest when you burn it.
When you burn it.
Any form of carbon that's burnt or any form of carbon essentially leads to carbon dioxide, and so does natural gas. I mean, so do we when we breathe in and out. The problem is methane. So methane is about 20 times as potent as a greenhouse gas as carbon dioxide is. And that's why a lot of methane flaring takes place, because instead of venting it into the air. So there are a lot of technologies in terms of which it can be captured rather than wasted into the environment. So that can be minimized by capture rather than simply venting or leakage.
Right, but I've heard that if only 2% of natural gas that's captured is leaked through pipage or fracking leakage or whatever, that it's done on all the good that's created by the efficiency of burning gas. Is that an accurate number?
I would have to look at the numbers, but it probably is an accurate sentiment in the sense that you don't want to leak a lot of natural gas. Natural gas is not difficult to contain. I mean, you don't want to leak any fossil fuel into the environment, but you're right in the sense that 2% of natural gas would be 40% of carbon dioxide being leaked into the air.
So how would you? I mean, how difficult is it to stop any leakage in the entire system?
I think technologies do exist, right? So we don't see big natural gas leakages in houses where we heat and cook and eat.
Yeah.
So the technology exists, and I think the industry has been fairly diligent in terms of preventing natural gas leakage, not necessarily by the most useful means. The one way that's done right now is just simply by flaring it and converting it into carbon dioxide and dumping that. So I don't see any technological challenges in terms of preventing that. There are technological challenges in terms of capturing it at the source and not burning it and using it for something else. But then there are chemists who are working on converting it at the source into other value-added chemicals, such as methanol, and people are even thinking of going all the way down to ethylene, and then it becomes a precursor for the petrochemical industry.
And thank you. I'll now recognize Ms. Fletcher for 5
I haven't yielded yet, but I'll yield back, Mr. Chairman.
Thank you, Mr. Chairman. Thank you. And I'll actually follow up on that question because I am interested in some of the technology surrounding the conversion of methane. Can you finish maybe answering that question or follow up about what you see as the most promising technologies for capturing methane and how you think that can address the concerns about methane emissions?
Okay, so I'm a mechanical engineer. I'm going to talk on the behalf of a chemist. This is actually technology coming out of a very brilliant chemist called Harry Gray at Caltech. He is, I think, well up into his 70s or early 80s, I don't know, and he's been working on catalytic conversion. So the idea between catalytic conversion is it's much less energy intensive than anything else, and he's been able to synthesize these new catalysts, which he creates in a plasma furnace. He tried to explain it to me, and I understood about 10% of it. But the idea is not only to convert methane, the idea is to convert methane, the idea is to convert carbon dioxide, and get to the point where you're simply pulling these things out of the air and converting them into value-added hydrocarbons up the chain using electrocatalysis.
And what phase of sort of research and development is this concept that he's developing right now?
I think he is maybe a few years from a desktop type prototype. So the idea behind these technologies is that they're very modular, and you could implement them at a lab scale, at a bench scale, on a skid pad that gets rolled out to a pad and be deployed. So they're not, the science has been proven, the technology is being developed, and they're fairly simple beyond this. Once you have the catalyst figured out, the rest of the technology is fairly simple.
Okay, thank you. And I have a general question kind of flowing from this for the panel. I know we have such limited time, but one of the things I was wondering about is how some of this technology and research is being developed and how industry has innovated or is working with some of the researchers to address some of these challenges.
Yeah, so I'm as a representing industry, we work with universities quite often on a lot of the grants and funding that we've gotten.
Could you turn your mic on, Dr. Bonner?
I think I have, so sorry. Yeah, so representing industry, we do work with universities quite often on a lot of the projects. With ARPA-E, for example, we're working with Lehigh University and University of Missouri to address various fundamental aspects of the technology. And I would say probably more than half of the technologies and programs we work on do involve university support.
And Dr. Weber, did you have a comment here too?
Yeah, I was to say that oftentimes our best advances from a society occur when there's collaboration across the different sectors. So we have industrial, academic, and government collaboration around projects, and that often happens, as Dr. Bonner mentioned. I think another aspect is to try to take these good ideas, develop and commercialize them, and there's different ways to do that. Creating more effective tech transfer offices at the national labs, which has been underway for decades, and also improving those systems for universities to get technologies out of the lab and into the field is useful. The larger companies in the energy sector, water sector, are really good at commercialization and scale up. They tend to be less good at the innovation, so they tend to collaborate with universities or acquire companies who are innovative to get there. So there's room for that, and the more we collaborate, the better it goes, is the short story on that.
Great, thank you. And Ms. Zerrenner, this perhaps ties into some of your testimony that I was able to look at before I was here in your written testimony. You talked about coordination between the energy and water sectors and said that we really need to update policies there. And so can you share your thoughts on how we can better kind of break down these silos between the energy and water sectors, encourage better planning between them, and work on some of these commercialization projects as well?
Sure. So a good example we have where the coordination really works is in San Antonio, where the municipally owned water and electric utilities plan alongside each other. They attend each other's planning meetings. They know that each is each other's biggest customer, and then they recognize that and follow through with that. So, for example, we have at a wastewater treatment facility in San Antonio biogas capture, and that uses that to power the wastewater. So that's on a very local level. But in the federal system, understanding, and I mentioned this in the oral testimony, understanding where the funding streams are across the federal government would be very helpful. At this point, I haven't seen anything, and when I was in the stakeholder process with DOE on the Energy Water Nexus roundtables, I talked about this as well, is that I haven't seen any across the government assessment or review of the different funding streams where they go into each. So you're looking at it as a comprehensive view. So the whole idea of the Energy Water Nexus is it's a system. So if we're not looking at it as a system, we're not addressing the systemic challenges. So the funding streams is really important because that also ties in then to the work programs. So also you want to know where all the programs are within the federal government, but you also want to know where the funding streams are. And I understand that committee process, you're going to have your appropriations subcommittee for water is going to be separate than energy, but wherever those cross coordinations can happen, I think that's really key. And some places where we don't tend to think of plugging in, like USDA, they have a big part to play in the Energy Water Nexus space. They need to be plugged into this, not just DOE, not just EPA. So we have USDA, USGS, that's another really important player in this space. There are a lot of places where this happens, and sometimes they could be really small. We're talking also about health impacts when we're talking about energy and water, so there may be some HHS issues that need to come up, and looking at a comprehensive across the government view, you may also find places where there are gaps that you need to fill. So I think that's a really critical piece.
Thank you, and I yield back my time.
Before bringing this hearing to a close, I do want to thank each of our witnesses for coming all this way and appearing before us today. We really appreciate it. The record will remain open for 2 weeks for any additional statements from the members and any additional questions the committee may ask of the witnesses. The witnesses are now excused and the hearing is adjourned. Thank you.